Hi students, we are going to discuss about thermodynamics and thermochemistry. Okay. So in this thermodynamics we have intensive property, extensive properties, state function, path functions, and we are going to discuss about work, heat and first law of thermodynamics, heat capacity related, and different type of isothermal process and adiabatic, isochoric, isobaric process and related graphs, and entropy for a phase change and mixing of gases and general expression for that one. Second law of thermodynamics, delta G, and the third law, and formation enthalpy, ionization enthalpy, neutralization enthalpy, resonance enthalpy, bomb calorimeter. These things briefly we are going one by one topic. Okay. So first thing what we have, intensive property, extensive property. So what is the intensive property and extensive property? Intensive properties are independent of amount of substance, so it cannot depend on amount of substance, and extensive properties are depend on amount of substance. So how we know that whether it is depend or independent? So if you are taking any substance, you divide into two parts. Okay, the property changes, then it is the which one? Extensive property. Property remains constant, that is the intensive property. Suppose I have taken 100 ml water, I divide into 50 ml and 50 ml. So volume is changing, initially 100, now 50, 50. Volume is a extensive property. If density, if you are taking both cases, density remains constant. So density is the intensive property. Okay, so like that we have intensive and extensive properties will be there. So intensive case we have temperature, pressure, surface tension, viscosity, E cell, and molar heat capacity, etc. will be comes under intensive properties. Extensive properties case, especially thermodynamic, delta H, delta G, internal energy change, entropy change, this all will be comes under extensive properties. Okay. Next we have basic definition, state function, path function. State function means it is dependent on only initial and final state. Okay. The internal energy change, entropy change, Gibbs free energy change, these all are comes under state function. Path functions are depend on path. Okay. So these are case Q and W will be comes under path functions that you have to get. And next topic we are going work and heat related. We know that this is the system we have. So heat will be go to the system or come out of the system like that. Here with respect to Q, it is heat into the system is a positive, out of the system negative. Okay. With respect to work, on this is on system will be positive and by system is a negative. Okay, so wherever it is outward, it is a negative inward, that is a positive you are getting. Okay, so work will be generally we are calculating P external into del V. Okay, V2 minus V1. And when you are taking your PV graph, okay, PV graph you are taking. So if they are showing that if it is a triangle, then work will be 1 by 2 AB. If it is they are showing square, then work will be equal to AB. And if they are showing that rectangle, so work will be equal to 1 by equal to A into B. If it is showing that P versus V graph, the cycle, this is the P2, this is the P1, this is the P1 and P2. In this case, the work will be equal to pi R square, that is equal to pi P2 minus P1 by 2, V2 minus V1 by 2, like that we can use. And so this modulus will be there. Sign convention you can, in PV case, if it is going clockwise, it will be work done by the system. This becomes negative sign. It is anti-clockwise, it will be showing a positive sign. Okay, the sign will be clockwise means if it is they are given clockwise, that is a negative sign. If it is giving anti-clockwise, that will be comes under positive sign we are showing. Okay, so this is about work and heat related expressions. Okay, and next we are going first law of thermodynamics. So first law of thermodynamics will be explaining what? So heat supplied to the system used to increase the internal energy and to do the mechanical work. So the heat supplied to the system used in two ways: to increase the internal energy, to do the mechanical work. This also we can write delta E equal to Q plus W. So these are the expressions you can write it first law of thermodynamics. Okay. So when you are applying this first law of thermodynamics to the different processes, suppose isothermal I am taking. In that case, isothermal process, internal energy change will be 0. In this case, Q equal to minus W. So heat supplied to the system will be to the only work done by the system. And adiabatic process case, Q equal to 0. Q equal to 0 means what happens? This delta E equal to W. Okay. Or this Q is equal to 0 means delta E comes this side, minus delta E is equal to minus W. That means by using internal energy, system will do the work. And isochoric process case, you have delta V will be 0, then work will be 0. Work will be 0 means what will we have? Delta E equal to Q at P, so constant value. And same way isobaric process case, delta P will be 0, and here you will get the expression delta H is equal to Q. Okay. So these are different processes we are applying the first law of thermodynamics. Okay, isothermal Q is equal to minus W, adiabatic process delta E is equal to W, and isochoric delta E is equal to Q. Isobaric case delta H is equal to QP. Okay. Next, we are going to the concept heat capacity related. Heat capacity related, what are the formulas will be there? First one, Q equal to Ms delta T. This is S will be the specific heat of the substance. Okay. And second one, Q is equal to Ml. It is latent heat of fusion. Case it will become. It is fusion means fusion, vaporization means vaporization. Okay. And the next one, you are getting the expressions CV, that is heat capacity at constant value. In case QV, you will get it. QV is equal to NCV delta T will become. So we already know QV is equal to delta H. So delta E is equal to NCV delta T will become. Okay, that is our formula. So this heat capacity at constant value. Same way constant pressure we are taking, then NCP delta T will become. From this one we can write delta H is equal to NCP delta T. Okay. So these are the formulas we will be using. Whenever the equilibrium will be there, you have to use the Q is equal to Ml expression. Otherwise, temperature changes as you have to use this one. So molar heat capacity at constant pressure. Okay, heat capacity at constant pressure will be give the delta H. Heat capacity at constant volume will be give the delta E related information. And we already know Cp minus Cv relation will be R will become. Okay, and different gases, monoatomic gas, biatomic gas, and polyatomic gas or triatomic gas. What is the Cp, Cv, and Cp and gamma? Okay, if you observe that Cp will become 3 by 2 R, this come 5 by 2 R. This is the Cp by gamma is equal to Cp by Cv, so 5 by 3. Same way, diatomic case, you have which one? 5 by 2 R and 7 by 2 R. This will become 7 by 5. This is the 1.4, this is 1.67. And polyatomic gases, this is a 3R, this is a 4R, and 4 by 3, that is equal to 1.3. Okay, so when gases are mixing each other, you have to find the Cv. Okay, resultant. So N1 CV1, N2 CV2 by N1 plus N2 you are doing means you will get a resultant CV. Then Cp you can find Cp plus R. So by using that expression Cp is equal to Cp plus R, then we can able to find out what Cp and Cv. Then we can able to find the Poisson ratio gamma. Okay, so that is the Cp Cv relations, heat capacity related relations, and expressions for mono, di, and polyatomic gases. Okay. Next. Next, we are going to discuss about important formulas related to isothermal, adiabatic, isochoric, isobaric. One by one, we will go through it. Okay. First one is the isothermal. Okay. First one, what we have? Isothermal process. Okay. Basically, whenever they are given isothermal at constant temperature, what is the things will be zero? Delta T equal to 0, temperature constant, delta T equal to 0, delta E equal to 0. Why is delta E equal to 0? For ideal gases, temperature, the internal energy directly proportional to absolute temperature. In that case, it will be 0, will be there. And also, del H will be also will be 0. Del H is equal to, you can, these two also you can express. Del E is equal to N CV delta T. So delta T 0 and Cp delta T, delta T will be 0. Okay. So these are common things, and also V2 by V1 is equal to P1 by V2. So this is the another point. P1 V1 equal to P2 V2. V2 by V1 is equal to P1 by P2. These are common expression we have. In this first case, we are seeing reversible process. Which reversible? Isothermal reversible process. In this case, what are the first formula we have? Okay, so we already know for isothermal process Q is equal to minus W, that is equal to 2.303 nRT log V2 by V1 or P1 by P2. Okay, so that is the first expression. And we already know delta E, delta H equal to 0. Other thermodynamic function delta S. Delta S is equal to delta S is equal to Q by T. Q is equal to this expression is there. So what will we get cancelled? T term will be get cancelled. N R log V2 by V1. Okay. Delta S we got. And the next one, delta S total if you take, this is a system related. Total means it will be 0. So surroundings will be minus sign will be come. And the next one, we have to find delta G at constant temperature isothermal process. That is minus 2.303 and R2 log V1 by V1 by V2 you will get delta G expression. Okay. So next, what we have? So we got del S, del G, also we got. Next we are going to discuss about irreversible process. Irreversible process. Irreversible process. In this case, you will get. In this case, you will get what work is equal to P external into del V. So we know that PV is equal to nRT and P external into V2 minus V1, that is equal to minus nRT and minus, okay, so V2 by that you get expression. Okay, that is the irreversible process related work. And Q is equal, we already know, minus 2. Okay, so that is a irreversible process in case of isothermal process. Okay, so we got almost all thermodynamic functions. Okay, delta E, delta H, delta S, delta G. Okay. Next, in this case, Next in this case, adiabatic process we are taking. Adiabatic process. So adiabatic process, what will be 0? Okay. So what will be 0? Or here Q will be 0, and we know that if Q equal to 0, the delta E equal to work. Delta E equal to work will be. In the first one, we are going reversible process. Reversible process. In this case, we have to find the expression for work. Generally, work is equal delta E is equal NCV delta T. This is the first expression you will get it. Or work is equal to, what you will get it? NR gamma minus 1 into delta T. Okay. So problems you have to find the temperature, T2 temperature, that is T1 into V1 by V2 gamma minus 1 minus 2. This will give the expression about T1 temperature, T2 temperature. So one temperature you know means volume changes we know means we can able to find the other temperature by using the delta T we can able to find out. And other than that, TV for gamma equal to constant and TV for gamma minus 1 equal to constant, and these two will be important for doing problems. So this is a reversible process case, you are getting this one. And what about delta S? Delta S system equal to delta S surroundings is equal to delta S total will be equal to 0 for this one. Okay. So that is a reversible process case. And next one we are going for irreversible process. So irreversible process, same work expression will be have the same. W is equal to minus P external into V2 minus V1 will become. And you have same delta E is equal to W. The expression you are getting. And sometimes they are asking expansion into vacuum. Expansion into vacuum or free expansion. It may be adiabatic process or isothermal process. Isothermal or adiabatic. Whenever P expansion is given, then P external will be equal to 0, then work will be 0 and heat will be 0, and delta E and delta H also will be equal to 0. So what will be not equal to 0? Delta S not equal to 0, delta B not equal to 0, and delta G will be not equal to 0. So this is related to which one? Expansion into vacuum or free expansion case, isothermal or adiabatic case, you can use it. Next one. Next, isochoric process. Isochoric process case, what will be constant? Volume will be constant. So del V equal to 0 and QV is equal to del E. That is the expression you will get, QV is equal to del E. And here work also will be 0 for this one. Okay. And the next, what is the other expressions you will get it? Mainly you have to see delta S system, that will becomes 2.303 and CV log T2 by expression you will get. Delta S surroundings will be minus of same thing. Delta S total will be 0. Okay. And in this process, if I am taking irreversible, any irreversible process, delta S total will be greater than 0. That is the second law of thermodynamics. Total entropy of the universe increases. For irreversible process, entropy will be always increases. Next one, we have isobaric process. Isobaric completed, isobaric process. In isobaric process, what will be constant? Pressure will be constant, P will be constant, and Q at constant pressure will be del H. Q at constant pressure will be del H will become. And here expression will become delta S to a system is equal to 2.303 NCP log T2 by T1, or delta S surroundings minus of this one. Delta S total will be 0. Delta S total will be 0 will be. And if I am taking irreversible process, delta S total will be greater than 0 will be. Okay. So this isobaric and isobaric process related. Okay. Mainly delta S expressions we require, and here isobaric process work also will be important. Next, graphs related if you take. We are starting from this one. Okay, so this is pressure versus volume. We are taking that expansion related. Okay, volume is increasing general. Okay, in this first one, pressure is constant. This is the isobaric process. This is the isothermal process. This is the adiabatic process. This one will becomes isobaric process. Okay, so this area under curve will be give the work done by the system. So in this case, isobaric will be have more work, then isothermal work, adiabatic work, then isobaric. Isobaric work 0 will be there. Same way, if you are taking a reverse. Okay, so we are taking compression. We are doing in this process. So this is pressure versus volume. So this volume pressure is constant, isobaric. This is isochoric. This one adiabatic and isothermal. Always adiabatic process have more slope. Okay. So here work maximum will be done in which process? Adiabatic and isothermal, then isobaric, isochoric will be 0. Okay. So this is another graph we are getting. And when you are comparing reversible work and irreversible work, this is the isothermal or adiabatic process, reversible work. And same way, you are taking this is the irreversible work. So here area under work will be, curve will be, maximum will be there. So W work done in a reversible process is greater than work done in irreversible process by system. On system is opposite will become. Okay, these are the graphs you have to see for different processes related. And the next thing we are going entropy from entropy. So entropy case delta S. Entropy is measure the disorderliness. Okay, randomness it will be measured. Delta S expression you have 2.303 NCB log T2 by T1 plus 2.303 N R log B2 by T1. Or we can also express delta S 2.303 NCP log T2 by T1 plus 2.303 NR log T1 by T2. These two expressions will become. Suppose if it is the isochoric process, this term will be not there. In an isobaric process, this term will be not there. Okay. So that is the expressions we are getting. During the phase change, delta S. Okay. So delta H by, suppose if it is a fusion, delta H fusion by freezing point. Delta S vaporization means delta H vaporization by T boiling point. Delta S phase change, transition is going on. So delta H transition by transition temperature. So like that, you'll get the phase change cases, you will get this one. Okay. When you are mixing the gases, del S will becomes minus 2.303 or sum over N1 log X centimeter when you are mixing the gases. Okay. So according to second law of thermodynamics, entropy of the system will be increases for irreversible process. Okay. So these are delta S terms related will be there. Okay. Next, what do we have? Delta G expressions. Okay. So delta G case, what are the important formulas are? We'll go through one by one. Delta G, you have first one. Delta G will be, if it is negative, it is a spontaneous process. If it is positive, it is a non-spontaneous process. If it is zero, it will be at equilibrium. Okay, and delta G and T delta S total relation, this one. Okay, delta G is equal to minus T delta S total. So in this case, if delta S total is positive, means this delta G negative, spontaneous process, and if it is negative, it is a non-spontaneous process. If it is zero, it is an equilibrium. Okay, so that is another relation, delta G, T delta S total. Okay, and the next one we have delta G is equal to delta H minus T delta S. Okay, so enthalpy change, entropy change. Okay. So what is the relationship of delta H, delta S, what happened to the delta G and spontaneity? This is a very important term. So it will be 4 cases will be possible. What are the 4 cases? Maybe this is negative, this is a positive, or positive, negative, or positive, positive, and negative, negative. Sometimes in exams, negative means they will give delta H will be less than 0 and del S will be greater than 0, like that will give the same expression. Okay. Here they both are, this is negative, first term is negative, this is positive, this term positive means positive into negative, negative. So second term also negative, first term also negative. So this value will be become negative, then it is a spontaneous, always spontaneous. Is an always spontaneous process. This is the opposite. This is positive, negative of negative, positive. So this total term positive. So always non-spontaneous will become. They both are positive means it may be positive or negative. So whenever temperature is greater than delta H by delta S, it is a spontaneous. Sometimes they will give high temperatures. It is a spontaneous. Both are negative means again positive or negative will become. So here T delta S delta H by delta S spontaneous. Maybe this gives low temperature. So equilibrium temperature means delta H by delta S. So only one thing you have to take. Delta H will be given units kilojoules per mole. Here it is given joules per Kelvin type. So that units you are taking in this one. This is a spontaneity related important topic in our NEET exam. Okay, now we got delta G, delta H, delta S relation we got. Next, what is the relations you have? Delta G is equal to minus NFBC. This is another relation we have. Same way delta G naught is equal to minus 2.303 RT log K equilibrium constant you are getting. So in this also further you can derive some more formulas from this point. So what are the formulas you can give? From this K is equal is the base 10. So delta minus delta G naught by 2.303 R. This is another expression you will get equilibrium constant related. Okay. And we know that delta G is equal to delta H T delta S. Okay. Now delta G is equal to, we can write minus 2.303 or T log K, the same term. From this log K, you will get it delta H naught, it's minus going that side, 2.303 or into 1 by T plus delta S minus become plus 2.303, this T get cancelled R. So this is like y is equal to minus mx plus. Okay. So the graph will become log K versus 1 by T like this. Another expression you are getting delta G expression. Okay. And delta G related points we have seen now. And if it is any chemical reaction is going on, delta G is equal for the reaction, delta G for the products minus delta G for the reactants. That is another one you can get it. Okay. Next, if you take third, if you take perfect crystal at 0 degrees Celsius, then the entropy will be remains constant. The change in entropy will be 0 will become. That will be the third law of thermodynamics. Okay. At 0 Kelvin, perfectly crystalline solid you are taking, the entropy will be constant. Okay. And now we are going important terms in thermochemistry. Okay, basic important terms we are going. First one, formation enthalpy. Standard formation enthalpy. Standard formation enthalpy. Okay. So this is very important while writing the expressions. First, when you are writing the standard formation enthalpy, so what are the main points you have to keep? You will get how many moles of product. 1 mole of product you will get it. So how many moles of product you will get it? 1 mole of product. The reactants are elements, not only elements, in standard state. These 2 points properly you have to remember to do the questions related to that. Okay. So you are getting 1 mole of product. Reactants from reactants what? Elements in standard state. Suppose I am taking H2 gas plus 1 by 2 O2 gas giving H2O liquid. Okay. So here H2 standard state is a gas, O2 standard state is a gas, H2O you are getting. So reactants giving 1 mole of substance. So it is a formation enthalpy. Okay, suppose we are writing this one 2H2O, O2 giving rise to H2O liquid. This is the reaction enthalpy. That is equal to 2 times of formation enthalpy. Okay, so this is not formation enthalpy because 2 moles you are getting. Okay. Same way, you are getting H2 gas plus Br2 gas giving 2 HBr. Okay, instead of that, we take 1 by 2. This also we are calling reaction enthalpy, not which enthalpy? Formation enthalpy. Because bromine standard state is a liquid, but here given gas. So that's why it is a reaction enthalpy. Same way, calcium oxide reacting with carbon dioxide and giving the calcium carbonate. You are getting 1 mole of product, but reactants are not elements and not, so that's why they are not comes under formation enthalpy. So 1 mole of product you have to get from its reactants. Reactants should be elements in standard state. That is the standard formation enthalpy. Okay. Suppose if you ask in any thing like carbon case, graphite is the standard. Okay. Hydrogen case, gas. Suppose we want formation enthalpy of methane, 1 carbon, 2 times hydrogen will be 1 mole of methane. gas. This is the formation enthalpy of methane, like that we are to write. Next, ionization enthalpy. Okay, suppose I am taking some weak acid, HA, it dissociate and give H plus ion and A minus ions. So here what is the enthalpy involved? That is called as the ionization enthalpy. To dissociate into its ions, the enthalpy change is called as the ionization enthalpy. And the neutralization enthalpy is strong acid, strong base case, they are reacting each other and forming water molecule. It is coming from strong acid, strong base, and we are getting 1 mole of water. In this case, the reaction enthalpy we are calling as a neutralization enthalpy. That is minus 13.7 kilocalories or minus 57.1 kilojoules. Okay, that is about 2H plus ions 2 times it will become, 3H plus ions 3 times it will become. Okay, this is easy one. And if you have strong acid plus weak base, okay, or weak acid plus strong base, or finally you are getting weak acid, weak base case. So in that case, how you can find the neutralization enthalpy? Okay, so in this case, delta H neutralization enthalpy is equal to delta H. If it is a strong acid, strong base is there, what is the enthalpy? That's delta H ionization enthalpy. Ionization enthalpy. How much? Ionization enthalpy means here enthalpy of ionization. Okay, so this weak base to dissociate, it required some energy that is a weak base related. Okay, same way delta H neutralization here for this weak base and strong base, weak acid and strong base case. Same delta H for strong acid, strong base plus delta H ionization of which one we are using? Which one is a weak one? A weak acid. So weak acid. Okay. Here delta H neutralization is equal to delta H strong acid and strong base plus delta H ionization of for weak acid, delta H ionization for weak base and weak acid. These are the points you have to careful related to neutralization enthalpy case when weak acids are involved or weak bases are involved. So delta H neutralization is equal to, if strong acid, strong base reacted, how much? Plus some energy, whatever they released, that will be used in for ionization. So that is the purpose we are writing delta H ionization. Okay. So that is the neutralization enthalpy. Okay. Now generally one double bond is there. Then what is we are going to discuss resonance enthalpy. So it will be, you are doing hydrogenation, you will get involve some energy. Okay, that is a X1. That is a delta H is equal to X1. What you will expect 3 double bonds means? What you will expect? Delta H is equal to 3x1. This is the expected one. But in reality, if you are taking benzene, you are taking 3H2, you are getting this one. You will get some energy, that is X2. Okay. So what is the resonance enthalpy? Resonance enthalpy here, expected del H minus observed del H. Here it is like 3x1 minus x2 will give you the resonance enthalpy. So expected enthalpy minus observed enthalpy change. The difference will give the resonance enthalpy molecule. Next, bomb calorimeter case. Okay, bomb calorimeter will be used to find del E. Okay, so del E, how they are finding? Molecular weight by weight into C into del T. This is the formula they are using to find the internal energy change. Okay, and once you know the del E, delta H you can find. Delta H is equal to del E plus delta Ng art. Okay. So del NGRT means number of moles of the product in gas phase minus number of moles of the reactant in gas phase. We can able to find out by using this formula. Okay, here del Ng will be positive, or del Ng will be negative, or del Ng will be zero. Okay, and in this case positive means what happens? This term become del H del E plus this one. In this case del H will be greater than del E. Negative means del E greater than del H, equal to 0 means del H equal to del E. This is the answer. So this is related to bomb calorimeter. And final and very important one is a reaction enthalpy. Okay, reaction enthalpy. So when we have to use product minus reactants, when we have to use the reactants minus product, that is the important one. So reaction enthalpy we are saying. Okay, so the data will be given different ways. Okay, so data is given in terms of combustion enthalpy or in terms of bond enthalpies or in terms of formation enthalpy. Okay, so the data is given in terms of data is given means suppose combustion enthalpy of carbon, hydrogen is this much and ethene is this much. So all combustion enthalpy is given. What is the combustion enthalpy for the following reaction? Means this one we have to use. All bond enthalpy, carbon bond enthalpy given, carbon hydrogen bond enthalpy given, this one we have to use. And formation enthalpy given means this one. So in this case, the delta RH, how you can find? Delta RH is equal, this is delta H for reactants minus delta H for products. Okay, suppose simple equation C plus H2 giving rise to C2H2. Okay, so for this one, what are the reactant? Carbon, graphite is a reactant, H2 is a reactant. So these combustion enthalpy, first you have to take minus this combustion enthalpy. Directly you will get the reaction enthalpy. And here delta RH is equal to delta H reactant side. Means you have bonds broken minus delta H per product side. It is a bonds formed. Okay. So if you are taking N2 plus H2 giving rise to 2NH. Okay, 3H2 is equal to 2NH3 is formed. In this molecule N triple bond N, this bond is broken. 3 times H bond is broken, and now 2 H lone pair. So here 6 NH bonds are coming, here the 3 HH bonds are broken and 1 triple bond broken. So this reactant side triple bond, 3 this energies you have to combine minus this 6 NH bonds case, how much will be released. So the bond enthalpy is given. So bonds broken minus bonds formed. You have to use a reactant side minus product side. And formation enthalpy given. Then you don't need to worry this. Directly you have to take as what? Delta H products minus delta H reactants. Okay. So if you are taking like CaO plus CO2 giving rise to CaCO3. This formation enthalpy of calcium oxide, carbon dioxide, calcium carbonate, all they are given. Then you can use product minus reactants. Okay. And suppose one more important point, delta H combustion of hydrogen. If the hydrogen combustion is going on, what will be formed? Water will be formed. So that is combustion enthalpy of 1 mole of hydrogen is nothing but formation enthalpy of water. Like that, also some useful conversions will be useful. Okay. So this way we can able to find the reaction enthalpies. Okay. So this is briefly about thermodynamics. We have covered intensive, extensive properties, work, heat capacities, their different thermodynamical process, entropy change, and Gibbs energy, and some thermochemistry terms we have seen. Okay, so thank you.